An array is an aggregate data type that lets us access many variables of the same type through a single identifier. Consider the case where you want to record the test scores for 30 students in a class. Without arrays, you would have to allocate 30 almost identical variables. Allocate 30 integer variables, each with a different name. Int test score student 1. Int test score student 2. Int test score student 3. Int test score student 30. Arrays give us a much easier way to do this. The following array definition is essentially equivalent. Int test score 30, allocate 30 integer variables in a fixed array. In an array variable declaration, we use square brackets to tell the compiler both that this is an array variable, instead of a normal variable, as well as how many variables to allocate, called the array length. Int test score 30, allocate 30 integer variables in a fixed array. Each of the variables in an array is called an element. Elements do not have their own unique names. Instead, to access individual elements of an array, we use the array name, along with the subscript operator, and a parameter called a subscript, or index, that tells the compiler which element we want. This process is called subscripting or indexing the array. In the example above, the first element in our array is test score 0. The second is test score 1. The 10th is test score 9. The last element in our test score array is test score 29. This is great because we no longer need to keep track of a bunch of different, but related, names. We can just vary the subscript to access different elements. Important, unlike everyday life, where we typically count starting from 1, in C++, arrays always count starting from 0. #include. Using namespace std. Int main. Int prime 5, hold the first 5 prime numbers. Prime 0 equals 2, the first element has index 0. Prime 1 equals 3. Prime 2 equals 5. Prime 3 equals 7. Prime 4 equals 11, the last element has index 4, array length 1. The lowest prime number is prime 0. The sum of the first 5 primes is prime 0 plus prime 1 plus prime 2 plus prime 3 plus prime 4. Return 0. Arrays can be made from any data type. Consider the following example, where we declare an array of doubles. #include. Int main. Double array 3, allocate 3 doubles. Array 0 equals 2.0. Array 1 equals 3.0. Array 2 equals 4.3. std. The average is, array 0 plus array 1 plus array 2, 3 \n. Return 0. When declaring a fixed array, the length of the array, between the square brackets, must be a compile time constant. This is because the length of a fixed array must be known at compile time. Here are some different ways to declare fixed arrays. Using a literal constant. Int array 5, OK. Using a macro symbolic constant. #define array length 5. Int array length, syntactically OK, but don't do this. Using a symbolic constant. Const int array length equals 5. Int array length, OK. Note that non-const variables or runtime constants cannot be used. Using a non-const variable. Int length. CIN length. Int array length, not OK. Length is not a compile time constant. Using a runtime const variable. Int temp equals 5. Const int length equals temp. The value of length isn't known until runtime, so this is a runtime constant, not a compile time constant. Int array length, not OK. Array elements are treated just like normal variables, and as such, they are not initialized when created. One way to initialize an array is to do it element by element. Int prime 5, hold the first 5 prime numbers. Prime 0 equals 2. Prime 1 equals 3. Prime 2 equals 5. Prime 3 equals 7. Prime 4 equals 11. However, this is a pain, especially as the array gets larger. Fortunately, C++ provides a more convenient way to initialize entire arrays via use of an initializer list. The following example is equivalent to the one above. Int prime 5 equals 2, 3, 5, 7, 11, use initializer list to initialize the fixed array. If there are more initializers in the list than the array can hold, the compiler will generate an error. However, if there are less initializers in the list than the array can hold, the remaining elements are initialized to 0, or whatever value 0 converts to for a non-integral fundamental type, e.g. 0.0 for double. This is called zero initialization. The following example shows this in action. Hashtag include. Int main. Int array 5 equals 7, 4, 5, only initialize first 3 elements. std_cout array 0 \n. std_cout array 1 \n. std_cout array 2 \n. std_cout array 3 \n. std_cout array 4 \n. Return 0. Consequently, to initialize all the elements of an array to 0, you can do this. Initialize all elements to 0. Int array 5 equals / initialize all elements to 0.0. Array 5 equals. If you are initializing a fixed array of elements using an initializer list, the compiler can figure out the length of the array for you. And you can omit explicitly declaring the length of the array. Int array 5 equals 0, 1, 2, 3, 4, explicitly define length of the array. Int array equals 0, 1, 2, 3, 4, let initializer list set length of the array. One of the big documentation problems with arrays is that integer indices do not provide any information to the programmer about the meaning of the index. Consider a class of 5 students. Const int number of students, 5. Int test scores number of students. Test scores 2 equals 76. Who is represented by test scores 2? It's not clear. This can be solved by setting up an enumeration where one enumerator maps to each of the possible array indices. Enum student names. Kenny, 0. Kyle, 1. Stan, 2. Butters, 3. Cartman, 4. Max students 5. Int main. Int test scores max students, allocate 5 integers. Test scores Stan equals 76. Return 0. In this way, it's much clearer what each of the array elements represents. Note that an extra enumerator named MaxStudents has been added. This enumerator is used during the array declaration to ensure the array has the proper length, as the array length should be one greater than the largest index. This is useful both for documentation purposes, and because the array will automatically be resized if another enumerator is added. Enum student names. Kenny, 0. Kyle, 1. Stan, 2. Butters, 3. Cartman, 4. Wendy, 5. MaxStudents 6. Int main. In test scores MaxStudents, allocate 6 integers. Test scores Stan equals 76, still works. Return 0. The size of operator can be used on arrays, and it will return the total size of the array length multiplied by element size. Note that due to the way C++ passes arrays to functions, this will not work properly for arrays that have been passed to functions. Int main. Int array equals 1, 1, 2, 3, 5, 8, 13, 21. Could. Return 0. You may get a slightly different result if the size of your types are different. In common usage, the terms array size and array length are both most often used to refer to the array's length. The size of the array isn't useful in most cases. Outside of the trick we've shown you above, starting with C++17, a better option is to use the stdsize function, which is defined in the header. Hashtag include for stdcode. Hashtag include for stdsize. Int main. Int array equals 1, 1, 2, 3, 5, 8, 13, 21. stdcode. Return 0. stdsize has the advantage of being easier to remember. It will work with other kinds of objects, such as stdarray and std vector, and it will cause a compiler error if you try to use it on a fixed array that has been passed to a function. Remember that an array of length n has array elements 0 through n1. So what happens if you try to access an array with a subscript outside of that range? Int main. Int prime 5, hold the first 5 prime numbers. Prime 5 equals 13. Return 0. In this program, our array is of length 5, but we're trying to write a test score into the 6th element, index 5. C++ does not do any checking to make sure that your indices are valid for the length of your array. So in the above example, the value of 13 will be inserted into memory where the 6th element would have been had it existed. When this happens, you will get undefined behavior. For example, this could overwrite the value of another variable, or cause your program to crash. You learned that the array subscript doesn't need to be a constant value, it can be a variable. This means we can use a loop variable as an array index to loop through all of the elements of our array and perform some calculation on them. This is such a common thing to do that wherever you find arrays, you will almost certainly find loops. When a loop is used to access each array element in turn, this is often called iterating through the array. Int scores equals 84, 92, 76, 81, 56. Const int number students equals stdsize, scores, requires C++17 and header. Const int number students equals size of, scores, 0, use this instead if not C++17 capable. Int total score equals 0. / use a loop to calculate total score. 4. Int student equals 0, student. Total score plus equals scores student. Double average score equals static cast, total score, number students. This solution is ideal in terms of both readability and maintenance. Because the loop does all of our array element accesses, the formulas adjust automatically to account for the number of elements in the array. This means the calculations do not have to be manually altered to account for new students, and we do not have to manually add the name of new array elements. Loops are typically used with arrays to do one of three things. 1. Calculate a value, e.g. average value, total value. 2. Search for a value, e.g. highest value, lowest value. 3. Reorganize the array, e.g. ascending order, descending order. One of the trickiest parts of using loops with arrays is making sure the loop iterates the proper number of times. Off by one errors are easy to make, and trying to access an element that is larger than the length of the array can have dire consequences. Sorting an array is the process of arranging all of the elements in the array in a particular order. There are many different cases in which sorting an array can be useful. Sorting an array can make searching an array more efficient, not only for humans, but also for computers. Because sorting arrays is so common, the C++ standard library includes a sorting function named stdsort. Stdsort lives in the header, and can be invoked on an array like so. #include for stdsort. #include. Int main. Const int length equals 5. Int array length equals 30, 50, 20, 10, 40. stdsort, array, array end length. 4. Int I equals 0, I. stdcode array I. Return 0. Because fixed arrays have memory allocated at compile time, that introduces two limitations. Fixed arrays cannot have a length based on either user input or some other value calculated at runtime. Fixed arrays have a fixed length that cannot be changed. In many cases, these limitations are problematic. Fortunately, C++ supports a second kind of array known as a dynamic array. The length of a dynamic array can be set at runtime, and their length can be changed. However, dynamic arrays are a little more complicated to instantiate. We can dynamically allocate arrays of variables. Unlike a fixed array, where the array size must be fixed at compile time, dynamically allocating an array allows us to choose an array length at runtime. To allocate an array dynamically, we use the array form of new and delete, often called new and delete. stdcode I just allocated an array of integers of length. Array 0 equals 5, set element 0 to value 5. Delete array, use array delete to deallocate array. We don't need to set array to null /0 here because it's going to go out of scope immediately after this anyway. Return 0. When deleting a dynamically allocated array, we have to use the array version of delete, which is delete. This tells the CPU that it needs to clean up multiple variables instead of a single variable. One of the most common mistakes that new programmers make when dealing with dynamic memory allocation is to use delete instead of delete when deleting a dynamically allocated array. Using the scalar version of delete on an array will result in undefined behavior, such as data corruption, memory leaks, crashes, or other problems. Dynamically allocating an array allows you to set the array length at the time of allocation. However, C++ does not provide a built-in way to resize an array that has already been allocated. It is possible to work around this limitation by dynamically allocating a new array, copying the elements over, and deleting the old array. Introduced in C++ 03, std vector provides dynamic array functionality that handles its own memory management. This means you can create arrays that have their length set at runtime, without having to explicitly allocate and deallocate memory using new and delete. Std vector lives in the header. #include. / no need to specify length at initialization. Std vector array. Std vector array 2 equals 9, 7, 5, 3, 1. Use initializer list to initialize array. Std vector array 3 9, 7, 5, 3, 1. Use uniform initialization to initialize array, C++ 11 onward. Just like std array, accessing array elements can be done via the operator, which does no bounds checking, or the @ function, which does bounds checking. Array 6 equals 2, no bounds checking. Array.at 7 equals 3 does bounds checking. Unlike built-in dynamic arrays, which don't know the length of the array they are pointing to, std vector keeps track of its length. We can ask for the vector's length via the size function. #include. #include. Int main. Std vector array 9, 7, 5, 3, 1. Std cout the length is, array.size. Return 0. Std vector can be used as a dynamic array, it can also be used as a stack. To do this, we can use 3 functions that match our key stack operations. Pushback pushes an element on the stack. Back returns the value of the top element on the stack. Popback pops an element off the stack.